Okay, so today we're going to be going over 7E. So this is um, the lecture before the next test. So just realize that the next time we meet, we're going to have a test. It'll be up in Blackboard. So today we're going to go over 7E. It won't take long, which is nice. It's kind of just some basic counting principles, which sounds like a very basic thing, but it's not going to be that basic. It's just basic probability counting principles. So this section actually starts on page four, 455. So 70 counting and probability. And the first thing he goes over is repetition. So what if we repeat something over and over and over, and how can we actually get the number of times or number of outcomes or arrangements, I should say. Let's talk about a basic example. If we looked at social security numbers, like how many social security numbers can we have, right? Let me auto tune that. Boom. So how many social security numbers can we have? And so what happens now? I'm going to assume that okay, let's do this. 1, 2, 3. Oh, we've got 9 digits in our social security number, right? 9 digits in the social security number. Now, I'm going to assume that any digit can be 0 to 9. I don't know if it can start with a 0. It might not technically be able to start with a 0. Well, let's say it can't. Let's say the first digit cannot be 0. Okay. So if we think about this, we've got 1, 2, 3. It's a dash, and then 1, 2, dash, 1, 2, 3. And I'm just going to write I'm going to write the number of options we have for each one of these numbers, right? So if the first number can't be 0, it can only be 1 through 9. That's 8 numbers. So the first number can be 8 numbers. And wait, there's a 9 numbers. Oh, sorry. 9 numbers. And the other options have 10 numbers. 0 through 9, that's 10 numbers. You've got 10 options for the rest of the numbers. So it's kind of easy to find this. If we want to know how many social security numbers, you just multiply this across. 9 times 10 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 times 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And what happens, because you're multiplying the same number over and over again, you can write that as an exponent, right? So this becomes 9 times 10 to the, this should be 8. Yeah, 10 to the 8. So whatever that, I mean, that's a big number, right? 9, and then we have 0, 0, 0, 0, 0, 0, 0, 0. So 900 million. We've got 900 million options for our social security number. So we're fine, right? Until we hit the billions. That seems wrong, but okay. Kind of nifty. So the same thing can be true if you, let's say you were looking at a menu. You're bored one day, maybe you're at a restaurant, you're looking at a menu, and you noticed that on the menu, you had to choose, let's say, an appetizer, and then you had to choose an entree, and you had to choose a side, and then you had to choose a dessert. Okay, so there's some meal, maybe it's like a wedding or something you have to go to, and you have to choose one from all 4 categories. And you notice for the appetizers, let's say there's like 4 options, right? You've got mozzarella sticks, you've got garlic bread, you've got something healthy like some sort of vegetable tray thing, and then you have I don't know, another appetizer that sounds good. Chicken wings. Okay. So you've got 4 options for your appetizer. The entree, though, only has, let's say, 3 options: fish, chicken, or steak. The side has 5 options, right? You've got 5 different sides to choose from. You can list them out if you want. And then dessert, let's say there were 2 desserts. Okay. Let me turn my phone off. and you're just wondering, I wonder how many options I really have for dinner combinations, right? How many different options I have for dinner combinations? Well, it's kind of easy to find. You just multiply these across. You've got 4 different appetizers times 3 different entrees times 5 different sides and times 2 desserts. And you wind up with, well, that's 10, that's 12, so 120. You've got 120 different combinations of dinners to choose from, really, for this example, which is kind of neat. You've got 120 different types of dinners. Okay. Oh, they did the one with the social security number in the blue. Oh yeah, and then they do one with that, like your license plate. Oh yeah, this is a good example. Let's do a license plate one. So in Arkansas, the normal license plate in Arkansas has 3 it's 3 letters first and then 3 numbers after. You can tell me if I'm wrong. I've got like a weird plate because it's like a school plate, but it's like 3 letters and then 3 numbers. And so if you're wondering, well, how many different license plates can we make out of this? Well, you got to think, well, how many different letters are in the alphabet, right? We've got, I think, 26 letters in the alphabet. So, and they can repeat, right? You could have like AAA or CCC. So it's going to be 26 times 26 times 26 times, right? And then the last 3 are 0 through 9, so 10, right? We've got 10 options for the last 3. So it's just 10 times 10 times 10. So 20, okay, oh man, I gotta do this on a calculator. Okay, so let me bust the calculator open. 26 times 26 times 26 times 10, times 10 times 10. And my calculator tells me we've got 17,576,000 options for license plates in this form, okay? In this form. We've got 17 million, I should say, 576,000 different combinations of license plates if it's in this form with 3 letters and then 3 numbers. Of course, if you add a number or add a letter, you're going to have a lot more options, right? If we add one more number, we'd multiply by another 10, right? So this would become 175 million instead of 17 million. So if they need to pump out some more letters, they can just, or more options, they can just add a number or a letter at the end, right? Or the beginning. Okay, well, and that kind of leads us to our first type of example, which is on permutations. So a permutation, by definition, it says we're dealing with permutations. This is on page 457. We're dealing with permutations whenever all selections come from a single group of items. No item may be selected more than once. So I'm going to just write that down. You can read the definition. Permutation. We have no order matters. That's what matters. The order matters. So we're dealing with permutations whenever all selections come from a single group of items. No item may be selected more than once. And the order matters. So the order of the arrangement matters. And they do an example where, look, A, B, D, C is going to be different than like B, A, C, D. Even though you're using the same exact letters, these are considered 2 different permutations, okay? Even though they're the same letters, they're the same permutations. We're like, kind of that example with the numbers before, like this might be the same dinner in a way, right? It's just, like, oh, you're getting the dessert first and then the appetizer second or whatever. So a permutation, though, the order matters. So if you see a group of letters arranged in these 2 different ways, even though they're the same exact letters, they would be considered 2 different permutations, okay? If every member of the group is selected in each possible permutation, then the total number of permutations possible is n factorial. So let's talk about that. So if n is the total, what do they use the word? Total number of members. And if we use all members, the total permutation is n factorial. Now, if you've never seen this exclamation point sign being used, that's fine. All it means is that you multiply descendingly, okay? So let's look at an example. It's kind of easier to do this with an example. Let's say we want all the different ways, hold on, all permutations of the letters ART. So we've got these three letters, ART, and we want all the different permutations of ART. So let's do this. So, I mean, if we think about this, your book kind of does a neat way of diagramming it out. It says, okay, let's say we have ART. We chose that first, right? Well, that means with the second letter, we can't use any letter twice, okay? So with the second letter, if I chose A first, the second letter either has to be T or R, right? For R, it's got to be A or T. And then for T, it has to be A or R, right? And now let's kind of go down this path here. If we do A and then T, well, now the last letter has to be R. If we do AR, the next letter has to be T, right? Because it hasn't been used. RA, we got to make rat, right? And then RTA, TAR, tar, and then TRA, tra, okay? And here's all the different permutations that have happened, right? If you follow each one of these to the end, we have all the permutations that have happened. Okay, so we've got, I mean, if you want to write them out, which is not bad if you only have three, but if you want to write them out, we've got ATR, right? That's that first line. The next one would be ART, RAT, RTA, TAR, and TRA. Notice these are all just arrangements of the same three letters, ART, right? And it's 1, 2, 3, 4, 5, 6 different arrangements, okay? This is the long way to find out how many permutations of 3 there are. The short way is to say, okay, if we're going to use all 3 of these letters in the permutation, we can just do 3 factorial. Now, what that means, again, the factorial symbol, this exclamation mark, means you just multiply descendingly. So we'd start with the number in front, and then we multiply it descendingly down. So 3 times 2 times 1, which times 1 is always itself, but 3 times 2 is 6. So we wind up with 6, which we knew that already. We did the long way, right? 1, 2, 3, 4, 5, 6. Kind of neat, okay? Kind of neat. Okay, so let's say, here's just a goofy kind of example. Hold on a second. I used to do this as a, hold on. Yeah. So let's say you're a librarian, you get a little bored, and you notice that all 7 of the Harry Potter books are on your cart to put back up in order. Okay, or not in order, but just to put back up on the shelf. So you got 7 Harry Potter books on the cart, and you get to think, I wonder how many different ways I can arrange these Harry Potter books. I'm bored. I'm taking this math class. It intrigues me. And I just want to know how many different ways I could actually arrange these 7 books. So let's think about this. Now, if we did the whole, kind of diagram, you'd have to start 1, 2, 3, 4, 5, 6, 7. And then 1, well, the next number after 1 could be, 2, 3, 4, 5, 6. It would just take forever, right? And you'd need a huge piece of paper. So instead of that, because we're using all 7 books, that's important for this example, We can only do the factorial thing if we're using all 7 of the books. We'll get to what happens if we only use like 4 or 5 of the books in a minute. But what if we're using all 7 of the books? We can just say it's that, and I apologize for that. But I'm going to have to just multiply it down. So 7 times 6 times 5 times 4 times 3 times 2 times 1, 5,040. So there's 5,040 different ways to arrange 7 items. Okay, for this example is Harry Potter books, right? But there's 5,040 different ways to arrange 7 items. Kind of neat. Well, now here I'm going to try to bleed in now probability. So let's say you're blindfolded, right? You're blindfolded in this library. All you've got in front of you are these 7 Harry Potter books, right? You have no idea what order they are, but we know there's 5,040 different ways to order them. What if you wanted to know the probability of arranging them in descending order or ascending order? Doesn't matter. We'll do descending order. Think about this. So there's 5,040 different ways to arrange them. There's only one way of getting them in descending order, right? So therefore, the probability of this occurring, we'll just say X, for X being the occurrence, would be 1 out of 5,040, okay? There's one way out of this 5,040 different ways of you actually getting this in order, right? So therefore, it is, let's look at this calculator, 1 divided by 5,040. There's a lot of decimals here. 0, there's a lot of zeros. 0.00198. We'll stop there. Okay. So if we want to write that as a percentage, you move it twice, 0.0198%. Pretty slim chance of you getting these ordered correctly in descending order. Now you double that if you were saying, oh, well, what about ascending or descending order, right? So there's 2 different ways to do that. Kind of neat, kind of interesting. I know you don't have to tell me. I know this stuff is intriguing. Okay. Your book does a few examples on this, and you're more than welcome to look at it. They are kind of neat. Like let's say, let's think of a good example of this. Oh yeah. Let's say you're at a swim meet. I think maybe your book did a swim meet one. Well, sort of it did a swim meet one. Okay, let's say you're at a swim meet. It's okay if you've never been to a swim meet. I don't know how many lanes there are, but let's say there's 8 lanes. So that means we have 8 swimmers, right? If there's 8 lanes. And you're thinking, I wonder how many different ways these 8 swimmers could finish, right? I mean, how many different ways, just randomly finish, right? Of course, in a swim meet, there's going to be some swimmers that are better than others. So the probability is a little different. Let's say the probability was all just randomized. And you're wondering, well, how many different ways could these 8 swimmers end? I mean, it could, if they're labeled by lanes, lane 2 could win, and then lane 4 could come in second, and lane 6 could come in third, and so on. But how many different ways could you end this? Well, again, because all 8 swimmers are swimming, it's going to be just 8 factorial, which we know 7 factorial. Look, I'm going to be a little lazy here. This is 8 times 7 factorial, right? 8 times 7 times 6. Well, that means we can say this is 8 times. We know this is 5,040. We did that in the last one. So cleared 8 times 5,040. 40,320, right? I mean, so if it was all random, the one outcome is 1 out of 4,320. Now, that's if all swimmers had the same ability and things like. I mean, we know some swimmers are going to be better, some are going to be worse, but just at random, it's going to be 1 out of 40,320 ways, which is pretty neat, kind of neat. Okay. So the question then pops up, well, what if we don't use all, this would be a good example. What if we don't use all of the swimmers, right? So what if, and we've got these 8 swimmers. This is actually the example, like the example your book uses. What if we've got these 8 swimmers, but only the top 3 medal, right? So how many different ways could the top 3 medal in an 8 swimmer race? So again, I mean, think about this. If we've got 8 swimmers, let's say they were all just labeled lanes 1, 2, 1, 3. We could have like 6, 2, 1, right? That where 6 came in first, 2 came in second, and 1 came in third. We could have 4, 8, 2, right? I mean, these are just examples where 4's first, 8's second, second is third, or 2 is third. Now look, we could have the same group here, but move them around, and that's a totally different permutation. Right? This is considered a different permutation. Even though the same 3 swimmers medaled, it's a totally different permutation. So the difference though for this one is we're only using the top 3. Even though we've got 8 swimmers, we're using the top 3. There's a formula for this, okay? And it looks like this. We actually label it this way. N permutate R. R is going to be the smaller group. N is the larger group like we used before. And it looks like this is on page 459, guys, if you're following along. It's n factorial over n minus r factorial, okay? N factorial over n minus r factorial. So for our example, it would be 8 permutate 3. 8 permutate 3. So it would be 8 factorial over 8 minus 3 factorial, because 3 is the smaller, okay? 8 factorial over 8 minus 3 factorial. So for our example, it would look like that. And then we've got to simplify it down, but that's what the formula is looking like, and that's how we're going to use it. So let's do that. So let's simplify it down. So this would be 8 factorial over, now 8 minus 3, just 5 factorial. 8 factorial over 5 factorial. And what's kind of easy on how to simplify these is you just multiply down until you get to the bottom factorial. So this would be 8 times 7 times 6 times 5 factorial, right? Because it would be 5 times 4 times 3 times 2 times 1. We've got 5 factorial on the bottom. Well, hey, guess what? Using another color here. These cancel out. So you wind up with 8 times 6 times 7. I'll put that in my calculator. $336. So this equals 300. So there's 336 ways that 3 swimmers could medal in an 8 swimmer race. Okay, there's 336 ways that 3 swimmers could medal in an 8 swimmer race. Kind of cool. Okay. Let's look at another one. Let's say we have a boat, right? And boats use flags for symbols, or for words, I should say. So let's say we've got 20 different flags that mean 20 different things, right? We've got 20 different flags that mean 20 different things, and their order matters here. Like a red, blue, and green flag would mean different than a green, blue, or red flag, okay? So the order matters when it comes to symbols. We want to know how many different arrangements of 4 flags for not messaging, whatever. Let's say just for the flagpole. Right. So we've got the flagpole going on, right? And we've got this, and we've got the different flags going on. We've got 4 flags. And we want to know how many different ways we can arrange them. And again, a red, blue, green, white is going to mean different than a white, blue, red, and green. The order matters for these arrangements, okay? And that's very important. We're going to get to when the order doesn't matter, but the order matters for these arrangements. So because it matters, we're going to use the permutation formula. So it's going to be 20 permutate 4. So 20 factorial over 20 minus 4 factorial. 20 factorial over 16 factorial. And again, we don't have to multiply 20 all the way down. We just have to get to 16 here. So 20 times 19 times 18 times 17 times 16 factorial over 16 factorial. So again, the 16 factorial cancels. And we just have to multiply 20 times 19 times 18 times 17. So let's see how many different arrangements we have here. Clear, hold on, 20 times 19 times 18 times 17. Holy cow. We have, excuse me, 116,280 arrangements. Wow. That's kind of neat, okay? So we've got 116,280 arrangements. Because when you change the order up on the flags, they mean a different symbol, right? Okay, the next type of grouping is called a combination. Combination, the difference is ordering doesn't matter, okay? This is on page 461, combinations. Order does not matter. So now if we look back, like how it would be different is if, like, say we did that swimmer example. So instead of saying, oh, how many different ways could the top 3 medal, it would be how many different ways could the top 3 not finish, but how many different ways could we get different groups of the top 3, right? Where, like, if 1, 8, and 9 finished in the top 3 for a combination. Okay, let's start that down. So if 1, 8, 9 finished in the top 3, well, 9, 8, 1 would mean the same combination, okay? And remember when we went back to that definition of permutation, these would be considered the same combination, but also like A, C, D, and B, and then B, A, C, and D. These would be considered the same combination because they're using the same letters, okay? This is a different permutation, but it's the same combination, okay? Order does not matter. So even though this order is different, it's still, in the eyes of the combination, it's the same exact thing, okay? Same exact thing. And the formula does turn out to be different with combinations. It's in combination R. And it turns out that it's n factorial. This is on the top of the page, 461, over n minus R factorial, which is the exact same as a permutation formula. But then you multiply the denominator by R factorial, okay? And what that does is it cancels out all the combinations, or really the permutations that are the same. This amount, by dividing out R factorial, you're canceling out all the common permutations, okay? All the common permutations. So let's look at an example. Let's say you were a teacher and you have, let's say, 12 students in your classroom. And you've got to choose 3 to go on a, let's say 2A convention, okay? You got to choose 3 to go to some convention. And, the order doesn't matter here. If you chose Larry, Joe, and Sally, that's the same as choosing Sally, Joe, and Larry, right? So this is definitely a combination because the order doesn't matter how you choose them. The same 3 are going to the convention. So this is going to be a combination. So it would be 12 combination 3. We want to know how many, really, the question is, how many different groups of 3 children could we use, right? How many groups of 3 could we send? So it's going to be 12 factorial over 12 minus 3 factorial times 3 factorial. And look, this will cancel out. So let's do this. Again, we're going to cancel the first part the same way we did before. 12 factorial over, now this is going to be 9 factorial times 3 factorial, right? 12 minus 9, or 12 minus 3 is 9. So this is going to be 12 times 11 times 10 times 9 factorial times 3 factorial. Okay, so here's how I'm going to cancel this. I'm going to use some creativity here. Now, the 9 factorial and the 9 factorial cancel. 3 factorial is just 3 times 2, it's 6, right? 3 times 2 is just 6. So this will cancel with that 12. It'll leave me with a 2 because 12 is just 6 times 2. So that means we would have 2 times 11 times 10, 220. So we have 220 groups of 3 if we start with 12 students, okay? We've got 220 groups of 3 if we start with 12 students. Here, I'll leave that cut out there to write it down. Now, another one, let's say you are starting a band and you guys know, let's say 10 songs. Okay, you know 10 songs. Maybe you released an album. That's not what happens anymore, but you put 10 songs on your SoundCloud, okay? And you know 10 new songs, or 10 songs, period. And you get booked for a gig, but the issue is, in the gig, look, they only need you to play for like 20 minutes, okay? 20 minutes, oh man, 6 songs, okay? We can play 6 songs at the gig. We don't get to play every single song on our SoundCloud, okay? We can only play 6 of them. Now, the question's got to be really important here. How the question's asked is important because, look, if the order mattered, if I ask you, look, I'll ask you this 2 different ways, actually. Let's say for A, I'm going to just say, how many different songs? Different, how would you write this? How many different groups of 6 songs? And then B, though, the order is going to matter here. So how many different set lists? So how many different groups of 6 songs? This doesn't matter. If you chose like the first 6 that you know, and then you mix them all around, but it's still just the first 6, maybe change the order up, this would be a combination. So this is going to be 10 combination 6. But how many different set lists is different? If you chose your first 6 songs, but then you ordered them a different way, that's a different set list, right? So therefore, the order matters for the second way. So it'd be 10 permutate 6. And let's see what happens. So 10 combination 6, this would be 10 factorial over 10 minus 6 factorial times 6 factorial. So this would be 10 factorial over 4 factorial, 6 factorial, right? Well, I'm going to just go down to 6 here. So I get 10 times 9 times 8 times 7 times 6 factorial. Now 4 factorial is 4 times 3 times 2. It's 24, right? Yeah. And then this would be 6 factorial. So these would cancel. I've got to get rid of the 24 now. Okay, let's think about, actually, this will all divide out. I'm just going to be lazy. I'm going to multiply the 10 times the 9 times the 8 times the 7. And I get 5,000. Oh, hey, yeah, we know that one. 5,040. And then we're going to divide that by 24. It'll divide evenly. You get 210. So there's 210 groups of 6, okay? There's 210 groups of 6 songs that we could choose. The second one, though, really is the number of different ways we could order those 6, okay? So this would be just 10 factorial. Now I'm going to be a little lazy. 10 minus 6 is 4 factorial. So you know what? I'm going to just find 10 factorial. 10 times 9 times 8 times 7 times 6. 6 times 5 times 4 times 3 times 2 times 1. That's 3,628,800. I'm going to divide that by 4 factorial, which is 4 times 3 times 2. That's 24. So that's 151,200. Holy cow, look how different that is. There's 151,200 different set lists we could make if we knew 10 songs, but we had to choose 6 to play, right? So that means, like, you know, if you knew song A, B, C, D, E, and F, this would be one set list, but another could be like A, C, B, D, E, and F. This would be considered a different set list because the B and the C were switched. Okay, that's why there's so many different. This is the same combination though, right? This would be considered the same combination. This is the different permutation. Okay, same combination, different permutation. Kind of crazy. Okay. Okay, yeah, I want you to read the last part about probability and coincidence in this section. And then, so for homework, it's going to be 1 through, actually, you don't have to do 1 through 63. You can do 1 through 57. So homework in 7E, 1 through 57 odd. Okay, 1 through 57 odd. That starts on page 464. Okay, let me bring this back to me. Okay, so Wednesday we're going to have our next test. I know it's kind of goofy having a test coming back from spring break. I would make sure to go back and look over everything leading up to this test. If you guys have any questions, please email me. I'll open it up on Wednesday for you to take. If you guys have any questions, let me know. If not,